Hello students, so today we are going to discuss a very important chapter, that is P block. In P block basically we are going to cover group 15 today, portion of group 16 we will cover tomorrow, and on Saturday we will complete the group 17 as well. So I am just going to point out the important reactions, okay, so because this is again a very big chapter, so we are just going to do the main reactions that are often asked in your JEE. For this chapter again you have to read your NCERT well, you need to know all the chemical as well as physical property and everything that is written in the NCERT. So NCERT reading is must for this topic, okay. So let's start the lecture. So the first thing which we want to discuss today is the preparation of N2. Now N2 has been asked many times in JEE Advanced as well as JEE Mains, and a lot of questions are there in BITSAT also. So this is again a very important reaction, okay. So if you consider the preparation of N2, you might be knowing it, okay, you might have memorized it as well for your board examination. Preparation of N2 can be done by heating ammonium salts, okay, by heating ammonium salts containing an oxidizing anion. Okay, so whenever there is a oxidizing ion along with ammonium ion, so it will always oxidize ammonium ion into N2. The common example is heating of NH4NO2. Okay, so if you heat NH4NO2, you get N2 plus H2O. Okay, so the oxidizing anion over here is nitride, it can be dichromate, it can be chlorate as well. Okay, so if you are having say ammonium dichromate, okay, now we know that dichromate ion is a oxidizing ion, so this will oxidize ammonium ion into N2. Cr2O3 we know is green in color, which we have done in transition compounds also, so we will form N2 plus Cr2O3 plus water. Similarly, if we heat ammonium chlorate, okay, so on heating ammonium chlorate we get N2 plus HCl plus water. Okay, so again a very important reaction. You might have seen many questions coming on this heating reactions, okay. So we can prepare N2 by heating ammonium salts. Ammonium salt should contain an oxidizing ion like NO2 negative, Cr2O7 2 negative or chlorate ion. So when you heat it we get N2, okay. So this is the main reaction, okay. Now one thing which you should remember over here is when you are heating ammonium nitrate, okay, ammonium nitrate on heating gives you N2O plus water, okay. So ammonium nitrate on heating gives you N2O and ammonium nitride on heating gives you N2. Now if you further heat N2O at a temperature greater than 800 degrees Celsius, so you can get N2 over here, okay. So this is a very important reaction. The next important reaction is by oxidation of ammonia, okay. So you can oxidize ammonia with copper oxide. When you react with copper oxide you will get N2 gas, okay. So ammonia on reaction with copper oxide gives us N2 plus copper plus water. You can similarly also react it with chlorine water or bromine water, okay. So it will form, chlorine water will form N2 plus HCl, okay, plus obviously water is there, so it will get eventually cancelled out. Bromine water, so you will get N2 plus H2O plus HBr. Hypochlorite, if you react it with NaOCl, so you will get N2 plus HCl, okay, plus water. Similarly, when you react with hypobromide, NOBr will get the same reaction, or with bleaching powder, okay. So these are very important reactions, okay. So I hope you must be knowing this, okay. This is the fundamental that everyone does in the N2 chapter, okay. So we are saying that suppose we want to heat ammonia with copper oxide, we will get N2, with lead oxide also we will get N2, okay, with NaOCl we will get N2, okay, with bleaching powder CaOCl2 we will get calcium chloride plus N2 plus water, okay. So all of these reactions ammonia is getting oxidized. So the two reactions that we have studied till now is heating ammonium salts containing an oxidizing ion and oxidation of ammonia by copper oxide, lead oxide, chlorine, bromine or NaOCl, NaOBr or bleaching powder. The next reaction is through the hydrolysis of through the action of HNO2 on urea. Okay, so we know this reaction which we have done in organic also. So when you react a primary amine with HNO2, okay, when you react a primary amine with HNO2, okay, just I will make you revisit it. We have done this in amines chapter. So when you react with HNO2, so basically a carbocation is formed, water attacks on it, forms alcohol, and N2 is released. So similarly, what will happen? There are two nitrogen over here, both will get released as N2 gas, okay, and there will be two OH that would be attached to C double bond O, forming carbonic acid. Carbonic acid is unstable, so we get CO2 plus water. So if you react HNO2 with urea, okay, if you react HNO2 with urea, you will get N2 plus CO2. Now this is again a very important reaction. If we want to get ultra pure, if we want to get the ultra pure nitrogen, okay, so ultra pure nitrogen is basically obtained by heating the azides, metal azides. So when you heat the metal azide, you get N2 and barium, okay. So you get only N2 gas, which is pure, which is even not moist, so you get the pure N2, okay. So when you heat a barium azide or sodium azide in a test tube, okay, sodium and the barium metal remains in the test tube, whereas only N2 gas is evolved out, so we are getting only one gas. And there is no moisture also, there is no water coming along with it, so the N2 obtained is ultra pure. So ultra pure nitrogen is prepared by heating sodium azide or barium azide, okay. So let us just quickly revisit it. So we are saying that the preparation of ammonia, okay, the preparation of N2 can happen by heating the ammonium salts, okay. So we are basically heating the ammonium salts containing a oxidizing anion like NO2 negative dichromate or chlorate. So we'll get N2 in all the cases, okay. When you heat ammonium nitrate, you will get N2. N2 on further heating above 800 degrees Celsius will give us N2. The next is the oxidation of ammonia. Oxidation of ammonia can be caused by copper oxide, lead oxide, chlorine water, bromine water, okay, sodium hypochlorite or bleaching powder. Similarly, the ultra pure nitrogen can be obtained by heating of the metal azides, okay. Next is the preparation of N2 from air. So commercially nitrogen is obtained by the liquefaction of air, because we know that in air we have a lot of nitrogen content, okay. The resultant liquid is fractionally distilled in a Claude's apparatus, okay. N2 having lower boiling point than O2 comes out as the first product, okay. So N2 is having lower boiling point than O2, okay. So when you heat it in, try to distill it in a Claude's apparatus, so we get N2 first, okay. Also we can do it by removing oxygen from the air, okay. So oxygen can be removed from the air by heating it with hot copper oxide. So what will happen if you take a purified air and react with hot copper oxide, we will get nitrogen. So with this, basically copper will react with the O2 that is present in the air and it will form copper oxide. So on heating with copper, oxygen is removed from the purified air and we are left with N2. Similarly, we will react purified air with hot coke, okay. So if any oxygen content is present, it will get converted into CO2 and CO and N2 will be left, okay. Similarly, if you are reacting the purified air with phosphorus, phosphorus will again combine with oxygen, will form P2O5 and nitrogen will be left. So we react this with water because this is also volatile. So this will also come along with N2. So we will react the mixture with water. P2O5 is a acidic oxide, it will react with water and form H3PO4, and in this way we will be getting N2. So N2 can be obtained from air, commercially it can be obtained from air. We have to react the purified air with copper, copper will remove oxygen, or react or heat the purified air with phosphorus, phosphorus will remove the oxygen as P2O5, further which reacts with water and gets converted into H3PO4. Similarly, we can react with hot coke, the oxygen present in the purified air will react with oxygen and form CO and CO2, okay. Next is the reactions of nitrogen. Now we already know that nitrogen is having a triple bond, okay. So nitrogen is combined with another nitrogen through a triple bond. The tendency of nitrogen to form a pi bond is very strong because the nitrogen orbital is small in size, okay. Nitrogen orbital 2p orbital is small in size, so it can effectively overlap with the other 2p orbital of the nitrogen atom and forming a strong pi bond. Due to this triple bond, the bond energy of n bond becomes very high, due to which this bond is chemically inert. So we say that N2 is chemically inert because of the strong bond between nitrogen and nitrogen. Okay. Now, if you go down the group, we say that nitrogen forms N2, but phosphorus in general does not form P2, it forms P4. Now, what happens is when we are going down the group, we know that when we are going down the group, the atomic size of the atom would increase. Now, when the atomic size increases, obviously its orbital size would also increase. Now, if you go to from nitrogen to phosphorus, phosphorus has the valence electron in the 3p orbital. So, on going down the group, the size of the 3p orbital increases. Now, the large orbitals do not overlap effectively during formation of a pi bond. So, because of ineffective overlap between the 3p orbitals, phosphorus pi bonds are not formed. They are very weak in nature. So, what happens, instead of forming a pp pi bond, okay, phosphorus pi bond, it catenates and gets converted into P4. So, if you go down the group, the tendency to form pi bonds decreases. Similar is the case with oxygen. Okay, oxygen forms a pi bond with oxygen. Oxygen is electronegative in nature. Okay, oxygen is having a small size, so its 2p orbital is small in size. So, it overlaps with the another 2p orbital of oxygen and forms a pi bond. But if you go to sulfur, sulfur exists as S8. Okay, so if you go to sulfur, so we know that sulfur pi bond would be weak. Okay, because sulfur valence electron is in 3p orbital. 3p orbitals are large in size and are diffused, so they don't overlap effectively to form a pi bond. As a result of which, sulfur catenates to form S8. Okay. So, if you look at this, nitrogen is inert, but if you consider the group 1 element, okay, we generally say that group 1 elements do not react with nitrogen. Okay, they do not react with nitrogen except lithium. Okay, now we know that lithium is small in size. So, if you react this with lithium, lithium will polarize the nitrogen atom because it is small in size. So, it will polarize the nitrogen atom and will break the N triple bond N. Whereas, if you go down the group, okay, lithium, sodium, potassium, rubidium, cesium, francium. So, if you go down the group, these metals have large size. Okay, because of the large size, they will not be able to polarize the nitrogen atom and they won't be able to break the N triple bond N. So, that is why we are saying that only lithium forms nitride and rest of the other elements of group 1 do not form nitrides. Okay, so this you have to remember that lithium on reaction with N2 forms Li3N. Okay, this is also known as lithium nitride, whereas other elements won't form any nitride. Okay, group 2 elements can easily form nitrides because if you compare it with group 1 elements, group 2 elements will be smaller in size. So, they are smaller in size, so they will polarize the nitrogen atom and they can break this triple bond and form nitrides. Okay, so if you look at magnesium, magnesium reacts with N2 and forms Mg3N2. Okay, lithium and magnesium is also having a diagonal relationship. So, you can also remember by this that magnesium reacts with N2 to form magnesium nitride. Okay, similarly, lithium will also react to form lithium nitride. Okay, rest of the group 1 elements do not react, whereas all the members of group 2 elements would react with nitrogen and form a nitride. Similarly, if you react this aluminium with N2, will get aluminium nitride. Okay, if you react with boron, you will get boron nitride. If you react with silicon, you will get silicon nitride. Okay, boron nitride you might have studied in the boron chapter. Okay, it is sometimes written like this. It is also known as inorganic graphite because its structure resembles that of graphite. Okay, hope this is clear to you. So, we are saying that we are reacting N2 with metals. So, in group 1 only lithium reacts to form lithium nitride. The rest of the elements do not react because their size are large. They will not be able to polarize the nitrogen and break the N triple bond N, because N triple bond N is having a high bond energy and is an inert bond which cannot be broken by the larger metals. If you go to group 2, all the group 2, group 3 elements will be able to react with nitrogen, okay, because they are smaller in size, they can polarize the nitrogen atom easily. Okay. Now, this again is a very important reaction. Nitrogen combines with calcium carbide, okay, it forms calcium cyanamide. Okay. So, calcium carbide reacts with nitrogen and form calcium cyanamide. So, calcium cyanamide is basically, okay, the structure of Cn2 negative is something like this, and the calcium is ionically attached to the nitrogen containing negative charge. Okay. So, this is the structure of cyanamide. Okay. So, when you heat calcium carbide with nitrogen, So you form CaCN2 plus carbon. Now this mixture is also known as nitrolim. You can see that the mixture of calcium cyanamide and carbon is technically known as nitrolim, which is also a fertilizers. Okay, they act as a fertilizers because when you dissolve this in water, they will give ammonia. Okay, they will give ammonia, and ammonia we know has a fertilizer property, so it can be used as a fertilizer. Similarly, if you react with barium carbide, so you will get barium cyanide over here. So there is a difference. When you react with calcium carbide, you get CaCN2, which is calcium cyanamide plus carbon. Mixture is known as nitrolim. But when you react it with barium carbide, it forms barium cyanide. Okay. Now one thing which you can also say that all these nitrites, okay, all the metal nitrites, okay, all the metal nitrites have N3 negative. Okay, all the metal nitrites have N3 negative, you can clearly see. So if you hydrolyze these metal nitrites, so we'll get metal hydroxide. Okay, just water will break into, okay, water can break into H plus and OH negative. So H plus will go to N3 negative and it will form ammonia. So when you react any metal nitrites, okay, when you react any metal nitrites with water, you will always get ammonia and metal hydroxide. Similarly, if you react calcium cyanamide with water, you will again get calcium carbonate plus ammonia. Okay, because ammonia is liberated out, we know that ammonia has a fertilizer property. Okay, ammonium phosphate, ammonium nitrate is having fertilizing property, so it is basically used as a fertilizer. Okay, hope this is clear to everyone. Okay. We say that it is chemically inert under ordinary conditions because of a strong N triple bond N. However, it shows chemical conductivity under high temperature. Okay, now we know that nitrogen combines with oxygen under the influence of high temperature like electric spark. So if you react N2 with O2 at a very high temperature or an electric arc, so we will get a nitrogen oxide. This is also known as Birkeland-Ayet process. Okay, nitrogen combines with hydrogen in presence of catalyst, finely divided iron at 200 atmosphere and 450 degrees Celsius to form ammonia. We know this is called as Haber's process. Okay, so this is your Haber's process and this is your Birkeland-Ayet process. Okay. So N2 reacts with O2 in electric spark or at a very high temperature to form NO. N2 reacts with hydrogen at high temperature and a high pressure to get ammonia. Okay. Now this is known as Haber's process. The catalyst here is iron and the promoter here is molybdenum. Okay. Okay, next comes is the again a very important reaction, that is ammonia. Nitrogen family is very important. Direct questions comes from preparation of N2, preparation of ammonia, oxidizing property of HNO3, phosphorus allotropes. Okay. So if you look at ammonia, so we can prepare ammonia by heating ammonium salts. Okay. So let us come to this point first, then we will see the other. So we are saying that whenever we are taking an ammonium salt and along with the ammonium salt a oxidizing agent or oxidizing ion is present, so ammonium ion is oxidized into N2. But when the anion is having a very poor oxidizing property or it is very less oxidizing in nature, then on heating you get ammonia. Okay. So anion here should be weak So anion should be weakly oxidizing. Okay, so if anion is weakly oxidizing, when you heat that, will get ammonia. Like you can take very clear examples. Ammonium hydroxide on heating will give us ammonia plus water. Okay, ammonium chloride on heating will again give us ammonia plus water. Now let us consider ammonium carbonate. Okay, again you can see that in carbonate, okay, carbon is in +4 state and carbonate is not a strong oxidizing, okay, agent. So on heating we will get ammonia plus H2CO3. Now H2CO3 gets converted into H2O plus CO2. Similarly, if you heat ammonium sulfate, so we will get ammonia plus H2SO4. Okay. if you heat ammonium hydrogen phosphate, you will get ammonia plus HPO3, okay, plus water. Okay, so when you are heating the ammonium salts in which the anion is weakly oxidizing, then we get ammonia. If it is strongly oxidizing example I have already given you, NO2 negative, ammonium nitride on heating gives N2, ammonium dichromate on heating gives N2, ammonium, okay, the last case which we did was ammonium chlorate on heating also gives us N2, okay. So you can just write it down, this is very important, okay. Next is the hydrolysis of nitrites. This we have already done. If you take say lithium nitride, so if you hydrolyze lithium nitride, so water breaks into H plus and OH negative, nitrites have N3 negative, so we'll get lithium hydroxide, N3 negative will gain 3 hydrogen and we'll get ammonia. Similarly, if you take say a group 2 nitride Mg3N2, so this has Mg2 plus and N3 negative, okay. So when you react with water will break into H plus and OH negative, N3 negative will take up the hydrogen and form ammonia and you will get magnesium hydroxide, okay. Similarly with ALN, if you hydrolyze them you get, okay, ALN is basically Al3 plus and N3 negative, so water will break into H plus and OH negative, okay. We need 3H plus to combine with N3 negative, okay, and 3OH negative will combine with Al3 plus because charges we have to balance. So we have to take 3 water, we will get aluminum hydroxide plus ammonia. Similarly, if you take boron nitride, react it with water, you get boric acid plus ammonia, okay. Similarly, if you react calcium cyanamide with water, okay, you get calcium carbonate plus ammonia, okay. So these are the few important preparations of ammonia, okay. So you can directly heat the ammonium salts or you can do the hydrolysis of nitrites, okay. So just look at these reactions. So basically what we are doing, by action of base or alkali on ammonium salt, so we are reacting ammonium nitrate with NaOH, so we know that a double displacement reaction would happen. Ammonium nitrate on reaction with NaOH would form ammonium hydroxide plus NaNO3, okay. So ammonium hydroxide would give us ammonia, okay. When you react ammonium sulfate with calcium oxide, now calcium oxide will react because it is basic in nature, so it will take out the sulfate ion and form calcium sulfate and ammonia would be liberated out, okay. This is a general method and used for the test of ammonium salt as well. So another reaction could be if you take urea, okay, and you react it with water or you react it with a base. So this OH negative goes and attack at the carbon, NH2 negative goes out and finally it forms ammonia. So we are going to form ammonia plus CO2 plus water, okay. So you can see that if you react urea with water, so this is basically an organic reaction, okay. OH negative goes and attack over here, so you form NH2 CO negative OH NH2, this negative pushes out the NH2 group and we form NH2 C double bond O OH NH2 negative. Now this NH2 negative will take up this hydrogen, will get NH2 COO negative plus ammonia, then again other water will attack and it will change into H2CO3, okay. Similarly, urea on treatment with caustic soda, if you react with NaOH, okay, same reaction, if you react with NaOH, we know that ammonia plus CO2 is formed. Now CO2 will react with NaOH because CO2 is acidic in nature and NaOH is basic in nature, so it will form Na2CO3, okay. Hope this is clear to you. Now next comes is the hydrolysis of calcium cyanamide, we have already done, urea with NaOH we have already done. Now next comes is the reduction of nitrates and nitrites, okay. Now this is also carried out by a alloy which is known as Devardas alloy, okay. Devardas alloy is basically copper, aluminum, zinc, okay. So nitrates can be reduced into ammonia and even nitrites can be reduced into ammonia using Devardas alloy, okay. So if you add Devardas alloy, that is a mixture of copper, aluminum and zinc, nitrate gets converted into ammonia, nitrite gets converted into ammonia. So if you look at this, you take reacted with zinc in basic medium. Okay, this is getting converted into ammonia. Sodium zincate is also being formed. If you react NaNO2 with NaOH and zinc, okay, they are the alloys in basic medium, so we are getting ammonia and sodium zincate. Okay, hope this is clear to you. Hope you know this reaction also. So let us just revisit the preparation of ammonia. We said that the ammonia can be prepared by heating ammonium compounds. Now these ammonium compounds should have an anion which is very less oxidizing. Okay, example is heating of ammonium chloride, ammonium carbonate, ammonium sulfate, ammonium hydrogen phosphate. Okay, so they on heating will generally give us ammonia. But if the anion is oxidizing like chromate, okay, chlorate or nitride, so they will get converted into N2. Okay, next was the hydrolysis of nitride. Okay, any nitride on hydrolysis will give us ammonia. Calcium cyanamide on hydrolysis will give us calcium carbonate and ammonia. Okay, the next important reaction was hydrolysis of urea. Urea can be hydrolyzed in water in basic medium as well. Okay, and a very important reaction, that is reduction of nitrates and nitrides. Okay, nitrates and nitrides can be reduced into ammonia by Devarda's alloy in basic medium. Okay, so if you react NO3 negative with zinc in basic medium, you get ammonia. You react NO2 negative with zinc in basic medium, you get ammonia. Okay, so hope this is clear to everyone. Okay, next very important question that have been asked in previous years, that is drying of ammonia. Now we know that whenever ammonia is being formed, it is quite possible that when it is getting liberated, water is also getting liberated simultaneously and ammonia might get moistened. So to remove that moisture, we have to add some dehydrating agent. Okay, now the common dehydrating agent are H2SO4. Now the next question comes, can we take H2SO4 or H3PO4 as the dehydrating agent, okay, or the drying agent for ammonia? Okay, now when you take these as the drying agent, now they are also acid. We know that ammonia is basic in nature. Okay, so ammonia is basic in nature. So if you take these drying agent, so there would be a reaction between acid and base. So ammonia would react with H2SO4 and form ammonium sulfate. Similarly, it could react with H3PO4 and form ammonium phosphate. Okay, with H2SO4 it would form ammonium sulfate. So this won't be used as a good drying agent because ammonia is getting consumed. So this is not a good drying agent. So H2SO4, H3PO4 cannot be taken as a drying agent in this case. Okay, now we know that calcium chloride is also a very good drying agent. Now calcium chloride is also not taken because when you try to dry ammonia, so basically what should happen, the water should be removed and ammonia should be free of moisture. But what happens when you take calcium chloride? Calcium fluoride forms a adduct or an addition product. So calcium chloride dot 8 ammonia, in many texts it is also written calcium chloride dot 2 ammonia. Okay, you can also take P2O5. P2O5 is also a drying agent. Okay, P2O5 removes water from any system and gets converted into H3PO4. So if P2O5 removes water from ammonia, it will form H3PO4. Okay, so we will get ammonia plus H3PO4. Now ammonia is basic and H3PO4 is acidic in nature, so they will react together and form ammonium phosphate. So we cannot take H2SO4, H3PO4, P2O5 or calcium chloride for drying of ammonia. Okay, so to dry ammonia we take calcium oxide. Okay, so to dry ammonia we take calcium oxide, or also called as quicklime. So quicklime is used as a drying agent for ammonia. Okay, so this is used as a drying agent for ammonia. Hope this is clear to you. Okay, next comes is the reducing property of ammonia. Now ammonia can be directly reduced into N2. Okay, so if you react ammonia with copper oxide, we get N2 plus copper plus water. Similarly, if you react ammonia with lead oxide, okay, so we get N2 plus Pb plus water. Okay, similarly, if you react ammonia with NaOCl, any hypochloride, so we get N2 plus, this we have done in the preparation of, okay, this we have just done in the preparation of N2. So you can also react with bleaching powder. Okay, and you will get N2 plus CaCl2 plus water. Okay, hope this is clear to you. Now there is one important reaction of ammonia. If you take ammonia and react with Cl2. Now if Cl2 is in excess, so what would happen here? NCl3 would be formed along with HCl. Now if you react ammonia with Cl2 in which ammonia is in excess, so if ammonia is in excess, so we'll get NH4Cl plus N2. Okay, again a very important reaction. Ammonia on reacting with excess of chlorine forms NCl3, ammonia on in excess reacting with chlorine forms NH4Cl plus N2. If you react this with iodine, so we get a NH3 dot Ni3. Okay, it is a brown explosive. Okay, so if you heat Ni3, you also get N2 plus iodine. Okay, so I hope this reaction is clear to everyone. This reaction is a very basic reaction that is there in the NCERT as well. Okay, next comes is the reaction with Nessler's reagent. So Nessler's reagent is basically used to test the ammonia or the ammonium ion in the solution. So Nessler's reagent is prepared by reacting Ki with HgCl2. So when you react Ki with HgCl2, you get HgI2. Now HgI2 is having a scarlet red color, okay, or it is basically red in color. Now when you react HgI2, okay, with excess of Ki, so when you react HgI2 with excess of Ki, you get K2HgIO4, okay, K2HgI4. So the scarlet red color dissolves and we get a K2HgI4. So the first reaction you should know over here is when you are reacting Ki with HgCl2. So HgI2 is formed, HgI2 is scarlet red in color. On reaction of HgI2 with excess of Ki, it forms K2HgI4. Now the alkaline solution of K2HgI4 is called as the Nessler's reagent. So K2HgI4 in basic medium, K2HgI4 plus OH negative is called as Nessler's reagent. Now when you react it with ammonia or the ammonium ion, we always get a brown precipitate of NH2.HgO.HgI. Okay, hope this is clear to everyone. Okay, so we get a brown precipitate of NH2.HgO.HgI. Okay, so Nessler's reagent on treatment with ammonia or ammonium salts give us the brown precipitate. Okay, so this is how we confirm the presence of ammonia. Okay, the next comes again is a very important parameter that is there in your qualitative analysis as well, that is reaction in aqueous medium. Okay, so suppose if we are taking copper 2 plus, okay, and we react with ammonium hydroxide. Okay, so we take copper 2 plus and we are reacting with aqueous ammonia. Aqueous ammonia means ammonium hydroxide. So we know that we will form copper hydroxide first. This is pale blue solution, okay, or intense blue solution. Now if you add more of ammonium hydroxide to this, so this precipitate dissolves and we get CuNH342 plus. Okay, generally when the precipitate dissolves, the color disappears, but this precipitate dissolves and we get again a blue color solution only. Okay, so initially on reaction with copper 2 plus we get copper hydroxide which is having a pale blue color. On further reacting with excess of ammonium hydroxide, the blue color precipitate dissolves and a clear blue color solution of tetraamine copper 2 ion is formed. Okay, similarly when you react this with cadmium 2 plus, so cadmium 2 plus on reaction with ammonium hydroxide gives us cadmium hydroxide, okay, which is white in color. When you react with excess of NH4OH, okay, when you are reacting with excess of NH4OH, so we'll get a complex over here. Now this complex does not have a color. Okay, basically we'll say that the white color precipitate dissolves in excess of ammonium hydroxide. Similarly, if you take zinc 2 plus, okay, if you react zinc 2 plus with aqueous ammonia or ammonium hydroxide, we'll get zinc hydroxide. We know that zinc hydroxide is a white precipitate, okay, on dissolving in excess of NH4OH, okay, we get Zn NH342 plus. So we'll say that the precipitate is now soluble. Okay, hope you have. Okay, so this is basically soluble. Okay, so this is basically soluble. So the precipitate dissolves and it gets soluble. Okay. Now if you react this with iron 3 plus, so iron 3 plus on reaction with aqueous ammonia, okay, gives us FeOH whole thrice. Iron 3 plus, we have generally said that it is brown in color. So this is basically brown in color, reddish brown in color. Okay. Now if you react this with excess of NH4OH, now this does not dissolve in excess of NH4OH. Okay. So iron 3 plus compounds are generally brown red, exception is FeCl3 which is yellow in color. Generally we say that iron 3 plus compounds are brown red in color, reddish brown in color, exception is FeCl3 which is yellow in color. So it does not dissolve in excess of NH4OH. Similarly, if you take iron 2 plus and react with aqueous ammonia, so you get FeOH whole twice. Iron 2 plus compounds are generally green in color. Okay, so when you react it with excess NH4OH, it does not dissolve. Okay, similarly, if you take Mn2 plus, you react with ammonia, so you get MnOH whole twice. Okay, in excess again this is Mn2 plus is basically having slight pink type of color. Okay, and in excess ammonium hydroxide, it does not give any, the precipitate does not dissolve. Similarly, if you take any silver salt, okay, if you take any silver salt, okay, I think you might be knowing this. If suppose we are having AgCl, okay, AgCl is basically a white color precipitate. If you take it in ammonium hydroxide, so this precipitate dissolves in ammonium hydroxide, okay, and forms this. Okay, so this, we say that this precipitate is soluble in ammonium hydroxide. Now when you take AgBr, AgBr is pale yellow in color. So when you dissolve this in ammonium hydroxide, so we'll say that it is getting converted into AgNH3 okay, Br. So we'll say that this is partially soluble. Okay, so the precipitate is partially soluble in ammonium hydroxide. But if you take AgI, AgI is having yellow color. Okay, now when you take it in ammonium hydroxide, it is insoluble. Okay, so this you must know. Okay, copper 2 plus forms COH whole twice, cadmium forms CDOH whole twice, white in color, zinc forms ZNOH whole twice, white in color, all of them dissolves in the excess ammonia. Iron 3 plus, iron 2 plus, Mn2 plus does not dissolve. AgCl, AgBr, AgI precipitate dissolves in excess ammonium hydroxide. Okay, there are many reactions that you might have done in your qualitative analysis. Okay, so this is basically directly coming from there. Okay, you can take a snapshot of this. Next comes is a very important, that is nitric acid. Nitric acid is also called as aqua fortis. Okay, sorry, nitric acid. Okay, so we say that this is prepared by Birkeland I8 process. Okay, so in Birkeland I8 process, what we do is we take a N2 initially and we react it with O2 in presence of high temperature or electric arc. The reaction is a endothermic reaction. So N2 reacts with O2 and forms NO. Now this NO is oxidized into NO2 by passing through compressed air. Okay, so NO get oxidized into NO2. Now this NO2 is acidic in nature. It is reacted with water. On reaction with water, it forms two acids, HNO2 and HNO3. Okay, so HNO2 obtained is further heated, which gives us HNO3 plus NO plus water. So HNO3 is generated, NO then again is reacted with O2 to form NO2, and this keeps going till we get HNO3. Okay, so if you look at this reaction, NO2 is called as a mixed anhydride because on reacting with water, it is forming two types of acid, HNO2 and HNO3. Okay, but if you take N2O5, if you react N2O5 with water, it will form HNO3. So it is forming only a single acid, whereas NO2 is forming two types of acid. Okay, also we know that N2 and NO are neutral. Okay, they are neutral in nature. Okay, this you have to read from your NCERT, the structures of various oxides, okay, their magnetic property. Only NO and NO2 are paramagnetic, whereas all the other are diamagnetic. Okay, and structures of all these oxides are also important, that is there in your NCERT. Okay, N2, NO2, N2O5 and N2O3. Okay, all of them are acidic oxide. So when you react this with water, you get HNO2. So NO2 is your mixed anhydride. Okay, the second important process for the preparation of HNO3 is Austral process. In Austral process, what we do is we react ammonia with O2. Okay, react ammonia with O2 in presence of platinum gauge. Okay, so you get NO plus water. Okay, so you get NO plus water plus heat. So it is an exothermic reaction. Now again, this NO formed is oxidized into NO2, then reacted with water to form HNO3, HNO2. Then HNO2 is again heated to get HNO3 and NO. So you can see that HNO2 is on heating is undergoing a disproportionation reaction. That is, same substance is undergoing oxidation as well as reduction. Okay, so HNO2 on heating disproportionates, giving HNO3 and NO. Okay. Now next comes is the oxidizing property of HNO3. Okay, so we know that HNO3 is a strong oxidizing agent. So when it acts as a strong oxidizing agent, okay, so it basically breaks into H2O plus NO plus nascent oxygen. So if you take dilute HNO3, okay, so dilute HNO3 generally oxidizes any other substance and itself gets converted into NO. But if you take HNO3 concentrated, okay, the concentrated HNO3, okay, this breaks into H2O plus NO2 plus O. So this causes oxidation. So whenever you are oxidizing any compound with HNO3, conc HNO3, you will get NO2. When you are oxidizing with dilute HNO3, you will get as NO. Okay. So we have already done similar type of reactions when we are doing K2CR2O7 and KMNO4. Okay. So the basic reactions remain the same. So if you take any iron 2 plus, okay, so if you suppose you are taking FeSO4 reacting with HNO3, okay, so HNO3 we know it is an oxidizing agent. Suppose we are reacting it with a conc HNO3, okay, so it is oxidizing agent. It will oxidize FeSO4 into Fe2SO4 whole thrice. As the number of sulfate ion is increasing, so we have to take H2SO4 as well. So FeSO4 on reaction with HNO3 and H2SO4 will give us Fe2SO4 whole thrice. Because HNO3 is concentrated, so NO2 gas is liberated. Okay. Similarly, if you react this with say SnCl2, okay, so SnCl2 tin is having +2 state. We know that tin is having +4 state as well, and +4 state is more stable than +2 state. So if you react SnCl2 with HNO3, okay, if you react SnCl2 with HNO3, so it will get oxidized into tin 4 plus. But along with HNO3, we have to take HCl because number of Cl is also increasing in the reaction. Okay, HNO3 will get oxidized into NO2. If you take say any hydrogen sulfide, hydrogen sulfides are generally oxidized by HNO3, conc HNO3 into sulfur and NO2. If you take any metal sulfide, okay, metal could be Pb, zinc, okay, so they get oxidized into metal sulfate, plus you will get NO2, okay. In all these cases we are using conc H2SO4. Similarly, you can oxidize NO2 negative, okay, so NO2 negative get oxidized into nitrate ion, okay. So if you react NaNO2 with HNO3, you will get NaNO3 plus NO2, okay. We are taking conc HNO3 in all the cases. Similarly, if you take arsenide, this will get converted into arsenate. Similarly, if you take sulfide, this would get converted into sulfate. Okay, so these were the basic reactions that we have done. Okay. Similarly, if you take Ki, if you take HX, okay, X can be chlorine, bromine, iodine, you react with conc HNO3. Okay. So conc HNO3 is a strong oxidizing agent. It will oxidize X negative into X2. So we'll get X2 plus NO2. Okay. Similarly, if you react this with Ki, okay, so Ki on reaction with HNO3, conc HNO3, iodine would be liberated out. Okay, so these are the few if you take any sugar or sucrose, okay, they generally get converted into carbon. So tar is formed. Okay, so this is the reaction with the compounds. So if you react these compounds with conc HNO3, they will get oxidized and NO2 is formed. Okay. Now this is a very basic reaction. Similar kind of reaction was there in KMNO4, K2Cr27. Similar reaction will also come in H2SO4 also. So you have to just remember the common species that are getting oxidized by HNO3, H2SO4, K2Cr27, KMNO4, ozone. Okay, so these are the important 5 or 6 oxidizing agent that you have to study. Now next comes is the reaction with metals. Okay, now this is again a very important portion. You might have like memorized this for your school examination as well. So when we react metals with very dilute acids, okay, if we react electropositive metal like magnesium and manganese, if we react magnesium and manganese with dilute acid, dilute HNO3, in that cases will evolve hydrogen gas. Okay, so in that cases will evolve a hydrogen gas and metal nitrate are formed. But with the rest of the other metals, different kinds of product are possible. So first we look for the general cases and then we will remember the specific or the exceptional behavior. So if you react, what I am saying, if you react with dilute HNO3, okay, dilute HNO3 will basically oxidize and itself get converted into NO. So if you react this with say PB, okay, so it will form PBO, okay, it will oxidize the metal and will form NO, plus obviously there will be water. If you react with copper, so it would be CuO plus NO. Similarly, it would react with cell Ag, it will form Ag2O plus NO. Similarly, if you react with Hg, it will form HgO plus NO. Okay, so these are the elements. So you directly react with dilute HNO3, you get these metals. Okay. Now, if you react with conc HNO3, so we know that conc HNO3 is also a strong oxidizing agent. It acts as an oxidizing agent and itself gets converted into NO2. So if you react this with say Pb, okay, Cu, Ag, Hg, okay, or even you can take zinc, okay, no, zinc here is not, zinc if you take, okay, even iron you can take. So all of them are oxidized into their metallic form, metallic oxide form, okay, and you get NO2 gas. So there is not such any exception with conc HNO3. If you take any metal, you react it with conc HNO3, the metals will always get converted into its stable oxidation state, okay, and it will form oxidized and NO2 is liberated. But dilute HNO3 on T20, lead, copper, Ag, Hg, they always give us NO. But if you take the two specific example, that is iron and zinc, okay, so you have to remember this iron, zinc and tin are the two, and even Hg in few cases are also the exception over here. So if you react iron with very dilute HNO3, okay, if you react iron or tin or zinc with very dilute HNO3, so in that cases you will get, okay, if you react this with very dilute HNO3, so you will get NH4NO3. Okay, so iron, zinc, okay, we can remember this as Fenzen, okay, I have remembered this as Fenzen, okay, iron and zinc, Fn and Zn, Fenzen on reaction with dilute HNO3. Fenzen means iron and zinc both have the common type of reaction. With very dilute HNO3 it forms HNO3, NH4NO3, okay, with dilute HNO3 they will form N2O and metal nitrates are formed, okay, and with conc we know that conc is, there is no exception, so with conc they will form NO2, okay, so you have to remember like Fenzen, iron, zinc, okay, iron with very dilute HNO3 gives us NH4NO3, okay, with dilute HNO3 we get NO, with conc, we get N2O, with conc we get as NO2. In general, dilute HNO3 when it oxidizes any compound it gets converted into NO, and if concentrated HNO3 oxidizes any compound we get NO2, okay, but only in the case of iron and zinc there is an exception, okay, so it is called as Fenzen, very dilute NH4NO3, dilute N2O and concentrated NO2. Rest other Pb, Cu, lead, copper, Hg, silver, Okay, they will react with dilute HNO3 to give us NO, and all the other elements when reacted with concentrated HNO3 they will always give NO2. Okay. Now another exception which you should remember over here is the tin. Okay. Even tin on reaction with NH4 dilute HNO3, very dilute HNO3 give us NH4N3. So you can remember this as phenzenes. Okay, phenzenes. Okay, so S stands for tin. Okay, so phenzenes, S stand for tin, so we'll get NH4NO3. With concentrated HNO3, okay, we know that tin oxide is amphoteric in nature. So with concentrated HNO3, tin will get converted into SNO2, which will further react with the water present in it and will get H2SNO3. So we get stannic acid, metastannic acid. Again the compound formed is the same, that is NO2. Okay. Okay. So just let us quickly do the reaction. Okay, just don't look at the table that has been given to you. So let us start with phenzene. Okay, phenzene. Okay, iron with dilute HNO3, very dilute HNO3, NH4NO3. Okay, iron with very dilute HNO3, NH4NO3 with dilute HNO3, N2O with conc NO2. Zinc on reaction with dilute HNO3, very dilute HNO3, ammonium nitrate, okay, with dilute nitric acid N2O with conc nitric acid NO2. Okay, phenzenes S. Okay, tin also on reaction with very dilute HNO3 gives us tin nitrate. Tin nitrate plus NH4NO3. Okay, so hope this is remembered. This is memorized now. So with conc, all the metals will give the metal oxide and metal nitrate and NO2. With tin there is a problem. With tin it forms H2SNO3, that is stannic acid. Okay, so with concentrated HNO3, almost all the acids are giving you, all the metals are giving you NO2, okay, and the metal nitrate, but only with tin you are getting, tin is converting into stannic acid. Okay, here again you are getting NO2 only. Okay, rest other with dilute, if you consider with dilute. Okay, so with dilute everyone Pb, Cu, Ag, Ag they give NO and the respective nitrate. Okay, there is again exception with tin. Okay, so tin on reaction with dilute HNO3 also gives us NH4NO3. Okay, so you have to remember this as phenzenes. Okay, so iron, zinc and tin does not follow a general specific trend. Okay, tin basically with dilute and very dilute gives ammonium nitrate. Okay, with very dilute they give NH4NO3, with dilute they give N2O, with concentrate they give NO2. Whereas with tin you say very dilute or dilute both gives NH4NO3, with concentrated tin gets converted into stannic acid. Okay, H2SNO3. Okay, hope you know this now. Okay, now if you react any elements, suppose you are reacting say sulfur with HNO3. Okay, so this would be the oxidation of the non-metal. So sulfur would be oxidized into SO2, further into SO3, and it would react with water because SO3 is a acidic oxide. It would react with water to form H2SO4. Similarly, if you react this with carbon, so HNO3 on reaction with carbon. So whenever you look at HNO3, the first reaction that should click in your mind is its oxidizing behavior. So HNO3 is oxidizing in nature, it will oxidize carbon into CO2. Now CO2 is acidic in nature, so it will take up water from the solution and will get converted into H2CO3. Okay, H2CO3 is wrong because H2CO3 gets converted into CO2 only. Okay, but if there is an option of H2CO3 and no option of CO2, then you have to go with H2CO3. Okay, similarly if you react this with iodine, so iodine gets converted into iodine gets converted into I2O5, which on reaction with water forms HiO3. Okay, so if you take sulfur, any non-metal, so they get oxidized into its acid. So this is the oxidation of non-metal. Okay, this would be the oxidation of metal. This is a general reaction, oxidation of the compounds, and this is the oxidation of metals. Okay, this is very important. Okay, direct questions are coming on this. Okay, hope this is clear to you. Now there are some metals which becomes passive on treatment with HNO3. That is, they do not react with HNO3 because an oxide layer is formed on their surface. As you react these metals with HNO3, the metal gets oxidized and a protective oxide layer is formed on the surface. So you can see that metals like beryllium, aluminum, chromium, iron, cobalt, nickel, okay, becomes passive in concentrated nitric acid. Conversion of reactive species into chemically inactive species is called as passivity. The passivity of these metal by conc HNO3 is due to the formation of a thin oxide layer on the surface of the metal, which prevents further reaction with the reagent. Because of this reason, in certain countries, aluminum vessels are used for carrying the nitric acids. Okay, so you can look at the okay, so this is these are the few metal that are passive. Okay, so you can remember this as okay, you can write this, remember something like this. Okay, FeCO, FeCO, FeCO means throw, FeCO anil. Okay, anil means aluminum and nickel. Okay, FeCO anil beryllium, or FeCO anil you can say at biscuit, FeCO anil biscuit. Okay, so FeCO Fe cobalt, ANIL means aluminum and nickel. Okay, B means beryllium. So these metals are becoming passive on treatment with HNO3. Now these are important, that's why we are trying to remember through mnemonics. So you have to write the mnemonics separately and you have to write what the mnemonic stands for and where it is used, so that you will be able to memorize them easily. Okay, so FeCO anil biscuit. Okay, so we'll say that iron, cobalt, aluminum, nickel and beryllium. Now there are some metals which do not react with nitric acid, but they will dissolve in aqua regia. So aqua regia is basically the mixture of HNO3 and HCl in the ratio 1:3. Okay, so noble metals like gold, palladium, platinum, iridium, rhodium do not react with nitric acid. So these are the metal FeCO anil biscuit, okay, that were not reacting with HNO3. Even all the noble metals, okay, we know that the noble metals like okay, platinum, gold, okay, platinum is there, gold is there, iridium is there. Okay, so they do not react with, even rhodium is also considered in the noble metal because it is used in jewelry. So these are not reactive with HNO3 and they are passive. Okay, so FeCO anil biscuit, iron, cobalt, nickel, aluminum and beryllium. Okay, noble metals like platinum, gold, rhodium, iridium. Rhodium, iridium is used in jewelry, so they are also in the noble metal category. They do not react with nitric acid. However, these dissolve in aqua regia. Aqua regia is a mixture of 3 parts of conc HCl and 1 part of conc HNO3. Okay, the enhanced ability to dissolve metal by aqua regia is due to the enhanced power of oxidation of nitric acid in the presence of chloride, and which forms complexes with the metal. Okay, so what happens over here is the oxidation power, the oxidizing power of HNO3 is enhanced, okay, by the H2SO4, okay, and the metal, when it gets oxidized, Cl negative basically reacts it with it, okay, Cl negative forms a complex with it and removes it from the solution. That's why reaction goes in the forward direction. So if you react gold, okay, so what is happening over here is HNO3 and HCl is reacting together. It is forming NO plus water plus Cl. Okay, now gold will react with Cl, the nascent chlorine that is formed. Initially it forms AuCl3. Okay, now this AuCl3 will react with HCl and form HAuCl4. So this is also called as tetrachloridoauric acid. Okay, similarly if you react with platinum, so platinum will react with 4 nascent chlorine initially and form PtCl4. PtCl4 will further react with HCl and form H2PtCl6. So this is also called as platinic acid. AuCl4 negative is also called as auric acid. Okay, tetrachloridoauric acid, tetrahexachlorido platinic acid. Okay, I hope you remember this reaction. So this is again very important. okay, the compounds which turns, metals which turns passive with HNO3 and which reacts with aqua regia, okay. So next comes is the hydrolysis. Okay, before going into the hydrolysis, let us just study the properties of the various allotropes of phosphorus. So basically we are having three kinds of allotrope. It is having more allotropes, but we are studying only three allotropes. The first one is the white allotrope, also known as the yellow phosphorus, okay. Then comes the red phosphorus. Okay, red phosphorus is something like this. Okay, then comes the black phosphorus. Black phosphorus is basically a hexagonal arrangement of the phosphorus atom, like graphite, okay. So it is a hexagonal arrangement of, okay, you can get these from your NCERT. So we are just going to study the property. You can see the ring is highly strained, this angle is 90 degree. Due to the strain, this is highly unstable. White phosphorus is highly unstable. The strain is removed, okay, when you remove one of the bond, and it basically forms a polymeric kind of system. Whereas in the red phosphorus, we are having a hexagonal ring, okay, that is again polymeric in nature. So the most reactive and highly unstable is white phosphorus. The most stable is black phosphorus, again because of the ring stability, you can say. Okay, so stability wise we will say that the most stable is black phosphorus, followed by white phosphorus, followed by red phosphorus, followed by white phosphorus. Okay, so if we look at the physical state, white is soft, waxy, okay, and brittle is the red phosphorus. So we have already said that this is white when pure, attains yellow color on standing. Okay, so this is always red in color. Okay, so white phosphorus is white, turns yellow, red is red in color. Odor, okay, so this is again important. White phosphorus is having a garlic odor, okay. So solubility in water, okay, these points you can just forget. Melting point of red phosphorus is more than that of, okay, white phosphorus. Solubility in water, white phosphorus is insoluble in water, red phosphorus is also insoluble in water. Both of white phosphorus is soluble in carbon disulfide, whereas red phosphorus is insoluble in carbon disulfide. Now white phosphorus is highly reactive. So if you take it in moisture, if you take it in air, so phosphorus react with O2 present in the air and gets converted into P4O10. Okay, so P4 white phosphorus is highly reactive. It reacts with O2 to form P4O10. So that is the reason why we store P4 in water. Okay, P4 does not dissolve. White phosphorus does not dissolve in water. It is insoluble in water. Okay, if it is in the water, it cannot come in contact with air and it cannot react. Red phosphorus is again insoluble in water. Okay, if you look at the carbon disulfide, white phosphorus is soluble in carbon disulfide, whereas red phosphorus is insoluble. Now you need to know these property. Okay, white phosphorus is highly poisonous in nature. Okay, if people operating in factories are exposed to white phosphorus, they get a disease known as phossy jaw, where the jaws of the jawline or the jaw bones get decayed. Okay, chemical activity, this is highly reactive, this is less reactive, this is unstable, this is stable. Okay, now another important property is white phosphorus glows in dark. Okay, so this property is called as chemiluminescence. Okay, whereas red phosphorus does not glow in dark. Okay, burning in air, this reacts spontaneously to form P4O10, that also react to form P4O10. Okay, reaction with NaOH. So when you react with NaOH, white phosphorus, you get phosphine. This does not have any reaction. Okay, action of chlorine, it forms PCl3 and PCl5. This also on heating will form PCl3 and PCl5. Reaction with hot conc HNO3, phosphorus we know is a non-metal. On treatment with HNO3, it will get converted into P4O10. P4O10 is acidic in nature, so it will react with water and form S3PO4. Okay, molecular formula it is P4. Now this is a complex polymer. Okay, so hope this is clear to you. Hope you know the structure also. So the important property that you should know is solubility. Okay, so we know that white phosphorus is insoluble in water, whereas soluble in carbon disulfide. Red phosphorus is insoluble in water and insoluble in carbon disulfide. Okay, white phosphorus possesses garlic odor, okay, and red phosphorus is odorless. This is highly unstable and very reactive, that is stable, but still it is reactive, we'll say it is less reactive. White phosphorus shows chemiluminescence, it glows in dark, whereas red phosphorus do not show chemiluminescence. On reaction with NaOH, this is a very important reaction, okay, P4 on reacting with NaOH. Now this P4 is a white phosphorus, it forms phosphine plus NaH2PO2. This reaction you might have encountered many times in your redox chapter while balancing disproportionation reaction. JEE has asked at least 10 to 12 times in last 40 years, advanced I am talking about, 12 times this reaction, 12-13 times has been asked. Okay, so this is again a very important. So they react with chlorine to form PCl3, PCl5. HNO3 is oxidizing acid, so P4 react with HNO3 will give P4O10, which reacts to form H3PO4. Now we know about the structure also. Okay, so black phosphorus is the most stable form. Next comes is the phosphine. Okay, so if you look at the structure of phosphine, so this is the structure of phosphine. So on reaction of P4 with NaOH, white phosphorus with NaOH, we get phosphine plus sodium hypophosphite. Okay, similarly we can get phosphine, okay, by reacting phosphides. Okay, so we have, if we are having phosphide, say we are having magnesium phosphide, similar to that of nitride. Okay, so this is having P3 negative, so this on hydrolysis will give us magnesium hydroxide plus phosphine. Okay, so magnesium phosphide on reaction with water gives us magnesium hydroxide and phosphine. Okay, so if you look at the physical property, phosphine has a odor of a rotten fish. Okay, it has a odor of a rotten fish. Okay, phosphine is again when heated in absence of air to 440 degrees Celsius or electric sparks are passed through phosphine, they decompose into red phosphorus and hydrogen. Okay, so they decompose into red phosphorus and hydrogen. So a pure substance of phosphine is spontaneously inflammable. It burns in air when oxygen is heated at 150 degrees Celsius. Okay, so this property is also used in the home signal. Okay, this you might have studied in your NCERT. Home signal is basically a mixture of calcium carbide and calcium phosphide. So whenever ships want to send the signal to the shores, so what they do is they take a can, in the can we are having calcium carbide and phosphide, they throw in the water. Okay, so the calcium carbide first reacts with the water, okay, and it forms calcium hydroxide and acetylene. Now this releases a lot of energy. Okay, now due to this phosphide which also is present over there, so phosphide also react with water and forms phosphine. Okay, so you can see that a mixture of calcium carbide and calcium phosphide is placed in metallic container, two holes are made and the container is thrown in the sea. Water enters and produces acetylene and phosphine. Okay, the gas mixture catches fire spontaneously due to the presence of P2H4. The acetylene produces a bright luminous flame which serves as a signal to the approaching species. Okay, so just you have to remember this, whenever you are forming phosphine through hydrolysis, you will always get P2H4 and that P2H4 appears as a vortex. Okay, so you have already studied in your NCERT written. Okay, so you get P2H4. Now P2H is highly flammable, so as phosphine and acetylene are formed, okay, in that can, P2H4 formed burns, and as the P2H4 burns, it provides the energy for the burning of acetylene as well as phosphine. So acetylene burns with a bright luminous flame and the approaching ship gets the signal. Okay, action of chlorine, if you react phosphine with chlorine, so it is basically getting converted into PCl5 and HCl. Okay, phosphine is neutral to litmus, however it is a weak base and weaker than ammonia. It reacts with HCl, HBr, Hi to form phosphonium ion. So if you react phosphine with HBr, HCl, Hi, it will form PH4X. Okay, if you react with nitric acid, we know that nitric acid is basically a oxidizing agent. Okay, so nitric acid when acts as an oxidizing agent, it will oxidize phosphine into P2O5, NO2 and water. Okay, if you look at the addition compounds, if you react AlCl3 with phosphine, you form AlCl3.2PS3, SnCl4 forms SnCl4.2PS3, CuCl forms CuCl.PS3. If you react with copper sulfate, okay, now when you are reacting copper sulfate with ammonia, so you are forming a complex CuNH3 4 2+, tetraamine copper sulfate. But when you react with phosphine, it forms copper phosphide which is black in color. Okay, So I hope you know this also. Okay, next comes is the oxy acids of phosphorus. Okay, so okay, I think someone is pushing the doubt. Okay, so let's do the doubt first. We'll discuss this tomorrow. Okay, we'll have to cover environmental chemistry tomorrow, so we'll just do in like 40-45 minutes, we'll just do the main points of environmental chemistry. Hope you have studied it from NCERT, and we are going to complete phosphorus, phosphoric acid, and we are going to take up a small portion of sulfur as well. Okay, we will be doing H2SO4, and on Saturday's lecture we'll just revisit halogens. We'll complete it in a go. Okay, so these are the chapter. I hope you have done it from your NCERT. Now the content in this chapter are like just too much, but you have to just concentrate on your NCERT, because NCERT is the book from where the JEE Mains questions are formed. Nitrogen is a very important family. You have to do it in a proper manner. You have to memorize all the reactions. Okay, so I will open the session for Q&A. Okay, so all the people who are having a doubt can send their doubt so that we can address your doubts. Okay, so just let me see the doubts. I have confusion between oxymercuration and demercuration hydrobonation reaction. Please explain mechanism clearly. Okay. Okay, Shiva. So if you are talking about oxymercuration, demercuration, okay, I am calling this as OMD. This is oxymercuration, demercuration reaction. So this is basically a Markov-Nikov addition without rearrangement. Okay, so if you take any alkene, suppose we are taking this as the alkene. Okay, so if you are adding dilute H2SO4 and adding water, so first H will get attached over here, will form a carbocation, there would be hydride shift and carbocation would be formed over here, then water will attack. But if you are doing oxymercuration, demercuration, so the first step you are adding mercuric acetate. Okay, so mercuric acetate basically, okay, I can write this as something like this. Okay, so you are taking mercuric acetate. So mercuric acetate first breaks into HgOAc plus acetate ion. Okay, so this reacts with mercuric acetate. Okay, so the mercuric acetate which we have taken breaks into Hg plus OAc. So this pi electrons attack on this electrophile. Okay, now because the pi bond has attacked at the electrophile, so both the carbon gets attached to the mercury. Okay, so this is what is formed initially. Okay, now what happens is we form a three-membered ring in which a metal is having a charge. Okay, so three-membered ring we know is unstable, so these rings generally go for ring opening reaction. So this bond is polarized over here. Okay, we can polarize this bond also, but if you polarize this bond, we'll get a carbocation over here. If you polarize this bond, we'll get a carbocation over here. Now we can clearly see that this carbocation is more stable because it will have more hyperconjugation as well as inductive effect. So this mercury polarizes over here, we get a carbocation over here. Now as soon as the carbocation is formed, it is attacked by the water. So there is no complete carbocation formed, that is why it cannot undergo rearrangement. So it is basically, it will break and the water will go and attack at this carbon. Okay, so there won't be any rearrangement possible. This was possible whenever a full carbocation was formed, that was with dilute H2SO4. Now if you react this with NaBH4 in the second step, now the second step of this reaction is not clear still now. Okay, so many text says that it can be an ionic mechanism, research also says that it can be a radical mechanism. So the stereochemistry of this reaction was not defined because the reactions can adopt different mechanism. So NaBH4 is basically a hydride ion, so hydride ion will attack at carbon and Hg will go out. So basically we were forming this. Okay, One thing which I'll say, this is not there in the syllabus, okay, so you don't have to go for the mechanism, you need to just know the reagent. The mechanism is never in the syllabus of JEE. So this is basically oxymercuration, demercuration. The first step is called as oxymercuration because oxygen and mercury are added in the first step, and in the second step, which is this step, this is called as demercuration because mercury is removed in this, okay. Now if you look for hydroboronation oxidation, now this is a very easy mechanism. So if you look for HBO, that is hydroboronation oxidation reaction. So we say that it is a anti-Markovnikov addition of water. Okay, so this is anti-Markovnikov addition of water. So what happens in this is, suppose you are taking any alkene and you are reacting this with B2H6 in presence of THF, and in the second step you are adding H2O2 and OH negative. So you will be getting a 1 degree alcohol, which is a anti-Markovnikov product. Okay. Now what happens in this reaction is, again, the first step is known as boronation. Okay. So basically boron is having hydroboronation, that is addition of hydrogen and boron. So these pi electrons are donated in the empty orbital of boron because boron is electron deficient. So the pi electrons are donated into boron. Now as soon as boron gets attached, okay, it always gets attached to a less sterically hindered carbon. Okay, you can also see that if you polarize this pi bond over here, you will get negative over here and you will get a positive over here. Okay, so this negative will be more stable because if you polarize the pi bond over here, the negative over will be unstable because of the inductive effect of the group. So what we are saying over here is boron gets attached to less hindered carbon. Okay, so it gets attached to less hindered carbon. Okay, now as soon as it gets attached, this boron will have now a negative charge. Okay, so this boron will have a negative charge because it's forming 4 bond. So hydride ion goes out and it is shifted to a carbon containing the positive charge. So in a step we say that hydrogen goes to the more sterically hindered carbon and boron goes to the less sterically hindered carbon. This is basically BH2. Okay, now because there are two hydrogens still left with the boron, so they can react with another alkene. Okay, this will donate hydrogen to this carbon, boron will get attached over here. So in this case we will be getting this. Okay, again it will react with alkene. Okay, and you will get, because it is again having one hydrogen, so this hydrogen is delivered to this carbon and boron gets attached to this carbon. So you basically form this over here. Now you can clearly see that boron and hydrogen have been attached in the same plane. Okay, so this is why we say that H and OH are also attached in the same plane. So this is basically syn addition of water. So in the first step you are getting hydroboronation product. Okay, hydrogen and boron is getting added. Now this R3B in the second step is reacted with H2O2 and OH negative, and it gives ROH plus H3BO3. Okay, I can also tell the mechanism of this one if you want to know. So this, what happens over here is H2O2 and OH negative reacts together. Okay, and they form this. Okay, now this oxygen negative goes and attack at the boron and it forms BRRROOH. Now this is having a negative charge. Okay, so an alkyl groups shifts to the oxygen and the OH is removed. So we get RBROR. Okay, R. Similarly, again another mole of H2O2 OH negative will attack. So it will convert all the R into ORs. Okay, and in the last step they will hydrolyze and form ROH, 3 moles of ROH and a mole of H3BO3. Okay, so this is the basic mechanism of hydroboronation oxidation. Okay, but again, Shiva, these are not there in the syllabus. Okay, these, if you wanted to prepare for Olympiad, go in the detailed mechanism, you can do this. But okay, for your JEE purpose, you just need to have the conclusion about the reactions. Okay, hope this is clear. Okay, next doubt please. On treatment of 100 ml of Rupesh Kumar. on treatment of 100 ml of 0.1 molar solution of COCl3.6 ammonia with excess AgNO3, 1.2 into 10 raised by 22 ions are precipitated the complexes. Okay, so this is the question of JEE Mains 2017. So we'll say that initial, we have been given a complex whose concentration and volume has been given to us. So we can say that the millimoles of complex would be its molarity into volume in ml. Okay, so molarity we know is 0.1 and volume we know is 100. Okay, so its millimole would be 10. Okay, so this is 10 millimoles, or we can write this as 10 into 10 raised to minus 3 moles. Okay, or in terms of number we can write this as into Avogadro's number, which is 6.022 into 10 raised to 23. Okay, so this is basically 10 raised to minus 2. If you multiply this, this becomes 10 raised to minus 21. So I can write this as 6 into 10 raised to 21. Okay, so number of complex molecule is this. Okay, hope this is clear to you. Now I can also write this as 0.6 into 10 raised to 22. Okay, now on reaction with excess AgNO3, obviously AgCl is precipitated out. So from this data we can understand that if there is only one Cl present outside the coordination sphere, okay, so we know that 1 mole of this complex is giving 1 mole of chloride ion. So 0.6 into 10 raised to 22 moles would give 0.6 into 10 raised to 0.6 into 10 raised to 22 number of complexes would give 0.6 into 10 raised to 22 number of Cl negative ion. Okay, but the number of Cl negative ion is 1.22 into 10 raised to 22. Okay, now if there is 2 Cl present outside the coordination sphere or in the ionization sphere, we know that now the 1 mole of this complex, okay, 1 mole of this complex would give us 2 moles of Cl negative ion. So these many number of complex would give into 2. So if we take these many number of complex, so this would give 1.2 into 10 raised to 22 number of Cl negative ions. Okay, so we'll get these many Cl negative ion. Now they will get precipitated as AgCl. So the moles of AgCl would be 1.2 into 10 raised to 22. So this matches with the data. So we can say that there are only 2 Cl present. Okay, now we have to maintain the coordination number as 6. Okay, so we'll take 5 water inside. Okay, cobalt 3 plus has a coordination number of 6. In JEE syllabus we have to basically study 6 and 4 coordination number. So 5 water should be inside. Okay, because there are 3 Cl, 1 Cl has to be inside, then only 2 Cls will be outside. Okay, so 5 water will be inside and 1 water which is remaining should be present outside. So this would be the answer. Okay, so this is again a easy question, Rupesh. So I would suggest you to go to the solutions chapter. Okay, solution chapter, as well as this is a concept of basic coordination chemistry. So you can go through such questions in the previous year, through the previous year paper. Also there are such questions in the daily practice problem sheet as well. You can solve that. Okay, so this is it for today. So we have done a very important portion today, that is N2, ammonia, okay, HNO3 and allotropes of phosphorus. So just remember all these 4, okay, important chemical reactions, their basic properties, okay, and the structures. We have missed out on some portion because that's how we will be dealing in crash course. We will not be able to do each and every finer points. So you have to take the NCERT, you have to study the physical property of all the group 15 elements. Okay, I hope you will do it by your own, and you have to look for the structures. Okay, the structures that are given in NCERT, especially the structure of nitrogen oxides and the oxy acids. Okay, rest we will do tomorrow. We will start with another theoretical chapter, that is environmental chemistry. So environmental chemistry doesn't have much of concepts, so it is basically the finer points, the important data which you should know in the chapter. Okay, so I would recommend you to read NCERT. If you have not read it properly, you have to keep reading it till your exam, because 80% of the question in JEE Mains will be there from your NCERT. It will not be there from any of the reaction mechanisms or any detailed mechanism of the reaction. It will basically stick to your NCERT. Okay, so this is it. We'll catch tomorrow for more interesting sessions. I hope everyone is using the YUP Master application now, and you are solving the daily practice sheets as well, and also giving the test that is being conducted on Sunday. Okay, thank you, students.